Hello, I'm Mathematics, and this is the wonderful world of combinatorics. So, in this video, we're going to be going over combinatorics, combinatorial functions, or in other words, binomials. So, let's start off with a problem. I've got two people, basically me and my friend. I'm person A, he's person B. So we've got person A here, we've got person A, and we've got person B. Now, me and him are planning to start a club. Me and person B are planning to start a club, and we need a president and a vice president. Now, in our club, somebody can be occupying many roles. So what I mean by that is I can occupy more than one role. And same thing, B can occupy more than one role. So I'm not limited to having one office. Now, the question is, how many ways are there to choose a president and a vice president from me and B, or person A and person B? Well, what we do is we say, well, first, let's draw a graph. So I'm going to draw a graph like this. I'm going to say we've got person A or person B. Now this is going to be for the presidency. So who's the president? Is it person A or is it person B? Let's say it's person A. Then who's the vice president? Is it person A or is it person B? No matter which one of these it is, we're done. So that's one case and two cases. Now we've got person B. In person B, we can have person A as vice president or person B as vice president. So we've got two more cases, BA, BB. So the cases we've got are AA, AB, BA, BB. And that's a total of 4 cases, or in other words, there are 4 ways to do this. Now this should make sense to you. There are 2 people, so there are 2 ways to choose the president. And then there are 2 people who can be the vice president, so there are 2 ways to choose the vice president. And 2 times 2, that's 4. Why multiply? Because for each of the cases of the first one, of the president, there are 2 cases of the vice president. So it's 2 times 2. Alright, now the question arises, what if instead of 2 people there were 5 people? Well, to do that, first I'm going to write one thing about these 2 people. I'm going to say we've got one slot for the vice president, one slot for the president and one slot for the vice president. So the way we did it with 2 people is we said there were 2 times 2. For 5 people, there's going to be 5 times 5. That's actually going to be 25. So if we had 5 people and we needed to choose a president and a vice president where a person could hold more than one office, then there would be 25 ways to do so. What if a person could only occupy one office? Then what? Well, what we would do is we would say, let's draw our graph again. And actually, let's take 2 people. Let's take 2 people and simplify this. So I'm going to draw my slots here. And let's draw a graph. We've got person A and person B. Person A can have A or B. Person B can have A or B. Except, not really. Person A can't be in 2 roles, and nor can person B. So, what did we just do here? Well, we said there are 2 people that can occupy the first role. So, we've got 2 people that can occupy the first role. Now, we would have 2 people that can occupy the second role, except consider this, there's a person who's occupying the presidency. The president can't be the vice president. So you're going to have to subtract 1 from the number of people that can be the vice president. Or 1. there's only one person that can be the vice president. Now, multiplying, we get 2. So let's try this with 5 people. And just to confirm, there is AB and there is BA. So now, just to confirm, let's try 5 people. If we've got 5 people, then there's 5 ways to choose our president. But one of these people is now a president, and they can't be the vice president. So there's only 4 ways now to choose our vice president. 5 times 4 is 20, and so there are 20 total ways to choose a president and a vice president. Now, in those 5 people, what if we wanted to choose 3 co-presidents? To simplify this, I'm going to start off with what if we wanted to choose 2 co-presidents, and then we'll work our way up to 3. So if we wanted to choose 2 co-presidents, that means that the order in which they were doesn't matter. The order in which they were picked, that doesn't matter. So if I chose person A first and then person B versus person B first and then person A, that's the same thing. So what you can see is if we chose person A first and then we chose person B and 5 times 4, and this should be clear to you why it's 5 times 4, that's the same thing as choosing person B first and then person A. So we've got to divide by 2 to get rid of that case. And in fact, to see why this is true, we're going to simplify it. We're going to go back to our 2 people case. So I'm going to start off with my node here. We've got person A, we've got person B, and then A, B, A, B. And here, what you'll see is we can't have this or this, but we also can't have this because AB is the same as BA. So we've got to divide by 2 because the number of ways to rearrange AB is 2. We can have AB or BA. So to get rid of the doubling, we've got to divide by 2. And you'll see we get 10. Now let's try with 3 co-presidents. So I'm going to erase this so that this is not in our way. Well, 3 co-presidents, that's going to be 5 for the first president, 4 for the second, 3 for the third, and then we've got to get rid of that doubling. Except, not really. There's not just 2 ways to rearrange 3 people. There's actually 6. If I had person A, person B, and person C, you will notice that I can have ABC, ACB, BAC, BCA, CAB, and CBA. That's 6. Now, how did I get 6 so quickly without trying it? Well, I did what's called a factorial. Basically, for my first slot, I've got 3 people. For the second slot, I've got 2 people. And for the third slot, I've got 1 person. Multiplying those together, you get 6, and we call this a factorial. In mathematics, we notate this as 3 factorial is equal to 3 times 2 times 1. And in general, n factorial is equal to n times n minus 1 times ... times 1. So if we wanted to choose 3 presidents, instead of dividing by 2, we should divide by 6, or 3 factorial. And when you simplify that, you're going to get 10. Wait, what? 10 and 10. We've got 2 presidents and 3 presidents. The number of ways to choose 2 co-presidents is the same as the number of ways to choose 3 co-presidents. That is, from 5 people. Isn't that strange? But when you think about it, when we're choosing 3 co-presidents, that's the same thing as choosing 2 non-co-presidents. And choosing 2 non-co-presidents is the same thing as choosing 2 co-presidents in mathematics. So obviously they're going to be the same. So now we're going to get into what is a combinatorial or a binomial. Well, a combinatorial or a binomial is basically what we just did. A combinatorial is what we just did. So when we were choosing those 3 people from 5, we were saying choose 3 from 5. And the way we notated this had to do with doing 5 times 4 times 3 divided by 3 factorial. In a combinatorial, we will say that this is 5 choose 3. So this is called, in English, we would say 5 choose 3. In math, we write it as open parentheses, 5 on the top, 3 on the bottom, no division symbol, no fraction, this is not a fraction, close parentheses. And this is called a binomial coefficient or a combinatorial function. So now we're going to get into what is a combinatorial formula. And the reason that we're going to get into this is because doing it by hand can be hard, and almost always a formula speeds things up. Now, the way I like to remember the formula is by doing 5 times 4 times 3 over 3 factorial, or basically n times n minus 1 times n minus 2 dot 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 times n minus k plus 1 over k factorial. That's the way I like to remember it. But that's not really the actual formula. The actual formula is like so. And I'm just going to write this and choose k. Oops, wrong color. And choose k. So we're going to say this is equal to this. But that's equal to, well, if we multiply this on the top, we multiply by n minus k factorial. And same thing on the bottom, n minus k factorial. Then that's going to be equal to n factorial over k factorial times n minus k factorial. And remember here, n minus k factorial over n minus k factorial is 1, so we're not changing the value. And this is actually the combinatorial formula. And the reason it's called a formula is because that's what it is. It's a formula. It's not something that should be memorized. You should know why it exists. And the reason why it exists is, well, we just showed it. So now we're going to get into Pascal's triangle. Now, Pascal's triangle, for those of you who don't know, basically works like this. You've got ones going down the left and ones going down the right. And the number of elements in each row is always increasing by 1. So you've got 1 element, 2 elements, 3 elements, 4 elements, so on and so forth. And for any element, that element is the sum of the 2 elements above it. So, as I have circled here, 4 plus 6 is 10. So the value of any element in Pascal's triangle is the sum of the 2 above it. Now, the only exception here is these on the sides, because they don't have anything above them. And Pascal's triangle goes on to infinity, which can be confusing sometimes, but it's not really that confusing when you just think, of course it goes on to infinity because it's an ever-expanding triangle. Now, Pascal's triangle has a lot of unique things about it. So, for example, Pascal's identity. Pascal's identity is basically an identification that, hey, binomials or combinatorials have a relation to Pascal's triangle. So let's take a look here. This is 1 choose 0. And if you don't understand how that works, how we can do choose 0, 1 choose 0 is basically the same way of saying from 1 person, I need to choose 0 people. And that's going to happen in 1 way. And so just a quick clarification, that's how choosing 0 works. n choose 0 is always equal to 1. So this is 1 choose 0, and this is 1 choose 1. Now this is 2 choose 0, 2 choose 2, 2 choose 1. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, 4 choose 5. 4 choose 1, 4 choose 0, 4 choose 2, 4 choose 3, 4 choose 4, 4 choose 5. Sorry. Let me say that one more time. I messed up twice there. 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. So on and so forth. So you'll see there's pretty much a direct correlation between Pascal's triangle and the binomials or combinatorials. So that's great. But what exactly does Pascal's identity tell us? Well, Pascal's identity says, well, it uses two things. First off, that each value on this list is a combinatorial. And the second thing is that each value is the sum of the two values above it. So let's say that this was n choose k. We would have n choose k. Then this would be n choose k plus 1. N choose k plus 1. And this would be n plus 1 choose k plus 1. N plus 1 choose k plus 1. And I'm just going to move this a bit lower. So now Pascal's identity comes in and says that, hey, this plus this is equal to this. So that means n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus n choose 1 n plus 1 choose k plus 1. And that's it. That's Pascal's identity. And that's one of the most important things about combinatorics. Pascal's identity forms the base for a lot of different formulas and quirks behind combinatorics. So one of them actually also deals with Pascal's triangle, and it's called the hockey stick identity. I won't give you a full detailed proof, but I will give you a gist of how it works. Take anything along this row. Anything. So let's say this one. I'm going to take this element. Then I can go down this column as long as I want. Keep going down, down, down as long as I want. And at a certain point, I can choose to stop. Now, I will have traversed these. So in this case, I've traversed 1, 4, 10, 20, 35, 56. So the sum of all of these is equal to this. And a better way to express this is like this. This is hockey stick identity. Basically says this plus this plus this plus this plus this plus this is equal to this. Now you can choose any number along this row. And you can go as far as you want. But it always remains the same. Mathematically, we say that this is n choose n plus n plus 1 choose n plus dot 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 plus n choose n plus k choose n is equal to, and I'm going to put this on the other side, n plus k plus 1 choose n plus 1. And your hint for how to solve this is to observe, and I'm going to go back to circling each of these, is to observe that n choose n is equal to n plus 1 choose n, and then use Pascal's identity to kind of filter down. So that is the hockey stick theorem. So if you want, you can pause the video now and try and prove this formula, but we are going to move on. And to the grid we go. The grid is basically kind of a set of problems that deals with combinatorics. And it's generally follows this kind of rule. From point A to point B on a grid, find the number of ways to traverse from A to B, basically. So on a grid, find the number of ways to go from A to B, where you only go up or to the right. Well, if you want, you can try this out. You can hand draw each and every single one of them. You would go this, then you could go this, then you could go this. But I'm going to already tell you, it may take you a long time to finish because there are 495 ways to go from A to B. So if you constantly draw out each of the 495 ways, first off, it's going to take you a long time and you're probably going to mess up somewhere. So there's got to be a much easier way to do this. There actually is. So first, let's take a look at any point. What we can see about this point is, to get to this point, I have to travel through this point, this point, this point, or this point. I have to travel through one of them. So the number of ways to get to this point is simply the sum of the number of ways to get to this point, plus this point, plus this point, plus this point. Because to get to this point, and then here, that's going to be the number of ways to get to this point. To get to this point and here, number of ways to get to this point, and you get the idea. There's no other way, is what I'm trying to say, to get to here without traveling through these. Except there's a slight problem. You actually can't travel through this or this. You can only travel through these. So we'll simplify it down. And now we'll get number of ways to go here is the sum of the number of ways to go to the point left of it and the number of ways to go to the point below it. Now obviously this won't exactly work for this edge right here and for this edge right here, but if you think about it, it kind of does, because if we take a point, for example here, the number of ways to get to the point left of it is 0, since there is no point. So it's simply equal to the number of ways to get to this point. So now we can try and fill this out. And we will. The number of ways to get from A to A is 1. And so we'll fill each and every one of these out, and similarly each and every one of these out. And these are all 1s because there's only one way to get to each of these. Then this is going to be 2, 3, 4, 5, 6, 7, 8, 9, and this is going to be 3, 4, 5. And we're going to keep on going. 6, 10, 15, 21, 28, 36, 45, and 10, 15. I'm going to take this eraser and just erase that. Then we're going to get 20, 35, 56. It's going to be 84. This is going to be 120. It's going to be 165. This is also going to be 35. 70, 126, 210, 330. This is going to be 495. Now remember earlier I said that this is 495? Well, that's exactly how I got it. This process is how I got 495. Now, obviously this is one way to do it. But for some ways, sometimes it's just not the best way. It can be too much of a work. So to do that, and so I want you to observe something from before. This was 495, and in fact, when we filled out this entire thing, you'll notice it was actually Pascal's triangle. That was Pascal's triangle, except rotated. And that's actually really useful because if you look, 495 is actually the 12th row, column 4, I believe, which is 12 choose 4. And if you go into your computer right now and type in 12 choose 4 in your calculator, you will get 495, which is really interesting. Why is that? Well, to do that, to find out, let's simplify this down. In fact, let's simplify it even more, where we just have a square instead of a grid. Now, what's the number of ways to get from point A to point B? that's gonna be one way. There's exactly one way to do that. There's actually two. Sorry, I misspoke. There's two ways. Sorry. There's two ways to get from point A to point B. And you could do that by just drawing it like I just did, or you could say, well, hey, I'm gonna say this is one way, so two ways. But if we look at it, actually this is just an up and a right. We just need to go up one, right one. And we need to find the number of ways to sequence up and right. Well, that's just, we've got two slots here. We've got two slots. And of those two slots, I need to choose one slot to put the U. And I need to choose as many slots as I need, basically, to put all of the U's. Because once I've placed every single U, the R's have to fall in their place. What I mean by that is, once I've placed all the U's, so let's say I had two U's, then I would place U, U, then the R's have no choice but to go in these spots. So the real number of ways to do this is actually just choose one spot from two spots to put the U, or 2 choose 1. That's equal to 2. So now what you'll notice is we can go to the big grid. In the big grid here, if we do this, we will get there's 1, there's 2, there's 3, there's 4. So there's 4 ups, 4 U's, and there's 1, 2, 3, 4, 5, 6, 7, 8. So 8 rights. That's a total of 12 slots, and of those I need to place 4 ups. So that's 12, choose 4. 12 choose 4 is going to equal 495, like we saw. Alright, so now here I'm going to challenge you guys. I want you guys to find this. What is 4 choose 0 the whole squared plus 4 choose 1 the whole squared plus 4 choose 2 the whole squared plus 4 choose 3 the whole squared plus 4 choose 4 the whole squared? Or equivalently, the bottom expression. So pause the video now and try and find it out. Did you get it? If you got 8 choose 4, you would be right. However, let's find out how we get this. To do that, I'm going to need a grid. And here is my grid. So let's take 4 choose 0. That's the number of ways to go 0 up and just go 4 to the right. Or just go to this point right here. Now 4 choose 1, 4 choose 1 is the number of ways to go 1 up and 3 right, or this point right here. Now 4 choose 2, 4 choose 2 is the number of ways to go to this point. And 4 choose 3, that's the number of ways to go to this point. And finally, 4 choose 4, that's the number of ways to go to this point. And now, let's go back to the start. 4 choose 4, that's the number of ways to go up 4, or to go to B. Now, 4 choose 3, that's the number of ways to go up 3, or to B. Now, 4 choose 2, that's the number of ways to go to B. And 4 choose 1, that's the number of ways to go to B. It's 1 up. And 4 choose 0, that's also the number of ways to go to B. So you'll see, this always takes us to B. This takes us to B, 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 and this takes us to B. And in fact, this is actually all of the ways to get to B. Now, the way I can say this is that if we take a look, to get to B, you'll have to cross this diagonal, because B is on this side and A is on this side. To cross the diagonal, that means you'd have to go through one of these points. And if you do go through one of these points, then you'll be counted in their individual expressions. So that's all the ways in which you can go from A to B. Now, these are the only ways to go from A to B. So what we can say is, well, that's just the same thing as, right, that's 4 up. That's going 1 up, 2 up, 3 up, 4 up, and 4 right. 1, 2, 3, 4, which is 8 choose 4. And if we do a quick calculation, 8 choose 4, that's going to give about, that's going to give us 70. Yeah. 70. Yeah, that's going to give us 70. 8 choose 4 is going to give us 70. So what we just So what we just saw was something called Vandermondi's identity. Vandermondi's identity is basically the original expression. It is n choose 0 whole squared plus, and then n choose 1 the whole squared plus dot 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 plus n choose n the whole squared. So that will always equate to, as we just saw, 2n choose n. Just to clarify, this is a special case of Vandermondi's identity. If you want to see more about it, you can go online and search up about Vandermondi's identity. Alright, thank you all so much for watching. Please don't forget to like and subscribe, and if you enjoyed, make sure to share this with someone else.